Okay, so here we have another sample problem. It says a solenoid has an inductance of 53 millihenry and a resistance of 0.37 ohm. If the solenoid is connected to a battery, how long will the current take to reach its half its final equilibrium value? Okay, so first we can try to calculate the tau L, which is the time constant, which is actually L over R. So it is so it is 53 milli. So 53 times 10 to the minus third power over 0.37 ohm. So this number is 143.2 milliseconds. Okay, so of course the answer is not this value, and we can slightly take a look at the equation for the current. It is like I equals E times E over R times 1 minus exponential to minus t, and then this is tau L, like this. So I just mentioned that when t equals 0, I equals 0, because this is 1, so 1 minus 1 is 0. So yeah, and when t equals infinity, I is E over R. So this question is asking that how long will the current take to reach half its final equilibrium value, which means that it asks you the time t equals what value, so that I is 1/2 of E over R, which means that we want half is equal to this factor. So we have 1/2 equals 1 minus exponential to minus t over tau L. Okay, so here we can just move this term over. So we have exponential to negative t over tau L equals 1/2. And then we take the reciprocal, so it becomes exponential to t over tau L equals 2. And then we can just take lateral log on both sides. So lateral log and exponential will cancel each other. So it becomes t over tau L equals lateral log of 2. So finally, t equals tau L times lateral log of 2, which is 133.2 times lateral log of 2, which is around milli. So which is around 0.1 second. So this is not difficult, but to apply the equation here and know what is the equilibrium and what is half of its equilibrium. Okay, so any questions? Okay. So next, here we talk about the energy stored in the magnetic field. Just like in chapter 25, when we learn the capacitor, we also discuss the energy stored in the electric field, or the energy stored in the capacitor. Here, the energy is stored in the inductor. So here it says if an inductor L carry a current I, the inductor's magnetic field store an energy given by this value, half of Li squared. So the derivation is like this: dUB, UB is the potential energy. UB is the potential energy in the B field. So dUB is the power, or you can regard this is dUB dt, or dUB, UBDT. Yeah. So actually DUBDT is the power, and then the power is always I times V. For the resistor, for the resistor only, you can have P equals I square R or V square over R, but P equals IV is true for different device, even though not resistor. P equals IV is still correct. So we have P equals IV, and then as I mentioned, V is LdIdt, so we have I LdIdt. So on both sides we have dt, so it makes it like dub equals IL di. Okay, so for the whole UB, which is integration of a dub from 0 to UB, and then we just plug in this one here, so it becomes IL di, and then L is a constant, so we just put it out. So finally it becomes integration of I di from 0 to IL like this. Maybe I should put a prime here to distinguish this I and this I. So taking the antiderivative of first order function, first order polynomial, it is I squared over 2. So we have I squared over 2 here. Okay, so this is the energy stored in the magnetic field, and comparing with energy stored in the E field, it is 1/2 C V squared, CV squared. So this is the duality between the B field, E field, and the inductor and capacitor. So similarly, you change this B to E, but yeah, actually it's just a variable name, and then you change from L to C or C to L. So C is a device generating E field, so L is the device generating B field. And then I just mentioned the voltage of a capacitor is continuous, and the current of the inductor is continuous. So this is the duality between them. Okay, so here we have another sample problem. It asks a solenoid has an inductance with same value, resistance with same value. Okay, so if a 12-volt EMF is applied across the coil, how much energy is stored in the magnetic field after the current has built up to its equilibrium value? Okay, so here nothing special. I equals E over R according to the Ohm's law, because it provides a DC source or the EMF. So it is 12 over the resistance 0.35. We can just ignore the inductance, because what it really asks is the equilibrium value. Where for the equilibrium value, which means that the current is constant, so dIdt is constant, and the voltage drop for the inductance for the inductor is also 0. So in this case, we can just regard the whole circuit is with a battery and a resistor in series. So it's like this. Okay, so this value is 34.38. And then it asks how much energy is stored in the magnetic field. Okay, so UB is nothing but 1/2 Li squared. So 1/2, and then L is 53 times 10 to minus third power, and then times 34.3 squared. So this is 31 joule. Yeah, 31 joule. So this is simple. For part B, after how many times constant will have this equilibrium energy be stored in the magnetic field? Okay, so here we would like to have UB to be UB half UB half to be half of the UB, half of the total UB. So on the left side, UB half is 1/2 Li half. Actually, I half is not half of the I, but actually we would like to know what is this I half should be, and then it should be it should be like this. 1/2 is on the right side. UB is we still have this 1/2, and then here we have another 1/2 Li squared, like this. So we can make some cancellation. This 1/2 cancel with this 1/2, and then this L cancel with this L. So we can see that I half should be 1 over square root of 2, because we have I half square here, we have I square here. So we take the square root on both sides. We have 1 over square root of 2I. So here we would like to know how many time constant, which means that we want to know the time when I half is 1 over square root of 2I. And if you still remember, maybe I just put it like I equals exponential E over R times 1 minus exponential to negative T over tau L, like this. So for I is exponential R, and then we would like to have I have to be 1 over square root of 2 times this one, which means that we would like to have this term to be 1 over square root of 2. So simply speaking, 1 over square root of 2 is 1 minus exponential to T half over tau L, like this. Because here I is E over R, so we like to have this one is 1 over square root of 2 E over R, so we need this term to be 1 over square root of 2. Okay, so we can try to solve this algebraic equation. Yeah, so similarly we can just move the terms over, exponential to negative T over tau T half over tau L equals 1 minus 1 over square root of 2, which is square root of 2 minus 1 over square root of 2. And then yeah, we can just take the reciprocal and then take the log, and then multiply tau L. So we will have T half is tau L times natural log of square root of 2 minus 1. Yeah, if I jump too fast, you can regard or take the reciprocal. So this is exponential to a positive exponent, and then we have the reciprocal, so that we have a square root of 2 over square root of 2 minus 1, which is this one. And then we can take the lateral log on both sides. So the lateral log and E will cancel each other. So the left side will become T over tau L, and then the right side will be lateral log of this term. So, and then finally we multiply tau L on both sides. So we have a T half equals tau L times the lateral log of square root of 2 over square root of 2 or minus 1. Okay, so this number is nothing but 176 millisecond. Or it asks you how many time constant, which means that this is the time constant, so this is the how many times, and we can say lateral log of square root of 2 over square root of 2 minus 1, which is 1.23 times. Okay. any questions? So here we also talk about the energy density stored in the magnetic field. Okay, so here, just go through this part, and then the UB, small UB is the energy density. So the energy density should be the energy over the volume. So the volume is the cross-section area multiplied by the length. Will be a cylindrical shape. So because this is an inductor, so it should have an cross-section area and with a length or a small l here. So A times L is the volume of this region. We assume the B field is uniform, although it is not actually the same, but we approximate the B field is uniform inside the inductor. So so it looks like UB is half of Li squared. So we have Li squared over 2 here, and then AL. And then we can slightly rearrange the term. So we have L over small l to be the first term, and then I squared over 2A here. Okay, so previously we already derived that the inductance per unit length is mu0 n square A for the solenoid, and then B is mu0 in. Okay, so we can have I equals B over mu0 n. Okay, so for this term we can just put it here. So we have this term here, and then for maybe use this, and then for this one we can replace the I here, so that we have B over mu naught n here, and then with 2A like this. Then we can do some cancellation. Okay, so this A is cancelled with this A, and then this mu0 is partially cancelled with this mu0 because we have mu0 square in the denominator. So we have mu0 here, and then we have 2 here, and then this n square with this n square will cancel each other. So the remaining one is b square in the denominator. So we have b square over 2 mu0. And if you still remember, the UE is 1/2 epsilon naught E squared. So this is also the duality. So for the E field and the B field, we change epsilon naught to 1 over mu naught, and then we change the E field to B field. So this is the duality for the energy density. Actually, we will use this expression in chapter 33 when we talk about the electromagnetic wave. Okay, so here we talk about the mutual inductance, or you can just regard it as a transformer. 变压器。Okay, so here, in the figures you can see we have two coils. This is the first one. This is the second one. And on the left figure A, we can see for the coil 1, we connect it to a battery with a resistance, so we can control the current going through the coil 1. So in this case, suppose this is the left side, this is positive, this is negative, which means that the current is going in this direction, like this, going to here, and then like this. Okay, so the current is something like this. Yeah, so according to the right-hand rule, we can determine the B field generated by this coil is point to the left side using the right-hand rule, because it is something like going to be here. So you can use the right-hand rule. You use your forefinger, follow the direction of current, and then your thumb point to the left side. Okay, so you can see B1 is point to the left side, and if we are changing the current by sliding through this resistor, then the magnetic flux going through the coil 2 is changing. In this case, the coil 2 will have its induced EMF. So it will have induced EMF. So actually we can just use a sensitive ammeter to really measure this induced EMF or induced current. Actually, for the lab session, the second lab you will do this lab. Okay, so here, if we don't connect the battery to the first coil, rather than that we connect the battery and the resistor to the second coil, yeah, so actually here the current will still going to the left side like this, and then yeah, the B field is also pointing to the left side using the right-hand rule. And then if we also changing the resistance, which means we're changing the current of this, so the magnetic flux going through the coil 1 is also changing. In this case, it will generate induced EMF and induced current. We can also use an ammeter to measure this induced current. So this is so-called the mutual inductance, which means that if we put two coils close to each other, if we provide changing current to one of the coil, then the other one will have induced current and induced EMF. Okay, so yeah, so varying is resistance and EMF is induced in coil 2 and blah blah. Okay, so here, rather than writing it like originally for self-induction, we write it as a EL equals negative L di dt. So we don't really need the subscript. Because it only refers to one inductor. But here we have one inductor and another two inductor and another inductor placing close together. So we will denote this one to be the first one, this is the second one. So here it means if we have the current going through the first coil, and if it is changing, then we rather than using L for the inductance, we use this to stand for the mutual inductance. And then the EMF is generated for the second coil. So this M is from coil 1 to coil 2, or similarly, if you have a changing current on coil 2, then with this same mutual inductance, it will generate EMF, induced EMF or induced current on the coil 1. So yeah, so this is the case here. And just now when we mentioned the the L will be n phi b over I. So this M could be m phi 2 1 over I1, or m equals n, should be n2, and here could be n1 phi 1 2 over I2, something like this. We will have a sample problem to discuss this point. And actually this one, so for sample problem 30.8, it says the figure shows two circular closed pack coils. So so the larger one is the first coil, and then the smaller one is the second coil. Okay, so here the smaller being coaxial, which means that they have the same center, and then the axis points to the same direction. So being coaxes with the larger and in the same plane. So derive an expression for the mutual inductance M of this arrangement of these two coils, assuming that R1 is much larger than R2. Okay. So here for the first coil, we connect the battery. We connect the battery here, so that there will be current going through the coil 1, and then it will generate B field, and then the magnetic flux for the coil 2 will be changing, and it will generate induced current and induced EMF for the coil 2. So let's see. When we consider the phi 2 1, which means that the magnetic flux generated to the coil 2 by coil 1. So here we should consider the B. The B should be B1, because B1 is the magnetic field generated by the coil 1. But the cross-section area should be A2, because we now consider the magnetic flux across the coil 2. So it should be B1A2. So here we will have M equals N2 phi 2 1 over I1, or at least in this problem we don't use, but you can also write it as N1 phi 1 2 over I2. Here we'll use this one. Okay, so in chapter 29 we have equation 29 36, not 36, 26, like BZ to be mu 0 I R square over 2 R square plus Z square to the 3 over 2 power. Actually, we have derived this equation, but we just use it here. And here, what we need to use this equation is at Z equals 0, because they are on the same plane. So we should keep this one. Of course, at that time we consider the B field when Z is much larger than R, so that we could just ignore R, and then we will have a Z to the 3rd power, something like that, to make it like the dipole moment. But here, because they are on the same plane, so we should still keep this term, and then we plug in Z to be 0. So in this case, B1 is N1 times B of 0. V of 0, which will be, so this one is 0, so we have R to the third power. Partly cancel with this one, so we have a 2R in the denominator, and then we have a N1 mu 0 I. So this is B1, and then we can calculate M to be N2 phi 21 over I1. So here phi 21 is this one, B1 times A. B1 is here. So phi 21 is this term multiplied by A2 and plugging it here. So we have N2 over I1, and then phi 2 is B1. This term is N1 mu 0 I over 2R, and then times A2. So this is phi 21. Then we can slightly rearrange the term. We get mu 0 N1 N2 A2 over 2R1 2R should be 2R1 this is I1. Okay, and actually this I1 and this I1 is cancelled. Okay, so this is the mutual inductance, and yes, something we can still plug in, because A2 is not a known variable from this equation. The known variable is the radius, so we should still plug in A2 to be pi R2 squared to plug in here. So we should plug in A to be here. So finally we should get M equals mu 0 N1 N2 pi R2 square, and then over 2R1, which will be pi mu 0 N1 N2 R2 square over 2R1. So this is the answer to this question. Okay, so the next part is that and actually at one point I need to mention is that for the question it says we assume that R1 is much larger than R2. So where we make the approximation is really at here. Actually the B field generated here is not uniform. This expression is only for the central axis. Which means exactly at the center point. But here we assume that R1 is much larger than R2, so that the approximation here is that we assume the B field over this small region is uniform, and in this case the phi 2 is approximately B1 times A2. Otherwise we need to do an integration, but B1 related to the R is not easy to find, so we make this approximation here. Okay, so here, what is the value for m when n1, n2, r2, r1 are this value? So we just need to plug in the number in this expression. Pi mu 0 mu 0 n1 n2 r2 square over 2 r1. Okay, so this is pi times 4 pi times 10 to minus 7, and then times 1200 square times R2 is 0.011. Okay, and then square all over 2 times 0.15. Okay, so this is 2.29 millihenry, which is quite large. Usually when we try to use some inductor on the circuit board, the value will be like nanohenry or microhenry level. So millihenry inductor is quite large, but yeah, regarding to this one, 1.2 centimeter, 15 centimeter, which is quite large. 15 centimeter is as large as this. Okay, so we have two additional examples. So this is the first one. A long coaxial cable consists of two thin wall concentric conductor cylinder with a weight A and B. The inner cylinder carries a static current A, and the outer cylinder provides the return path for that current. Okay, the current set up a magnetic field between the two cylinders. Calculate the energy stored in the magnetic field for a length L of the cable. Okay, so this is so-called a coaxial cable, which is used for transmitting high frequency data. Actually, if you just use a single wire to transmit signal, then the signal will attenuate fast. But yeah, for high frequency data, just like HDMI cable or whatever, they probably, or something we use something like SMA cable, then it should be so-called a coaxial, which means that one of the cylinder is for the signal to go, and then the other one is for the return path, so that the signal can will not disturb itself. It will not disturb itself. Okay, so here we would like to use the Ampere's law, mu 0I. So this is the Ampere's law. So we need to calculate the energy stored in the magnetic field. So first we need to calculate the magnetic field generated by this cable. So we should have a B times 2 pi R, as what we have previously discussed before. B is constant, so B times the circumference of the Ampere loop. So B times 2 pi R on the left side, and on the right side it is mu 0I. So we get B equals mu 0I over 2 pi R. And of course, this R is between the inner and outer cylinder. And here, small ub is B squared over 2 mu naught. And then B squared. So we have mu 0 square and then I square over 2 pi square will be 4 pi square, and then multiplied by 2 will be 8 pi square. and then we also have a mu 0 here, and then r squared. So mu 0 and mu 0 squared can be cancelled, so we have mu 0 I squared over 8 pi squared r squared. So finally, we need to do the integration. And before that, we can write it as a dUB. So this is capital letter, capital U, which stands for the total energy. The total energy will be UB, small ub times the small volume. So this is the volume. Okay, so it becomes mu 0 I squared over 8 pi squared times r, and then dV. And then this r, this dV should be mu 0 I squared 8 pi r pi squared. So this one should be dr d theta dz for the cylindrical coordinate. Cylindrical coordinate. Okay, coordinate. Okay, so which is somehow like constructing a polar coordinate with the z-axis. So which is like the polar coordinate. The cross-section area for the polar coordinate will be r dr d phi d theta, and then this dz is just perpendicular to the plane. So this is nothing but dz. Okay, so here we can calculate the total UB with the integration. Okay, so this is nothing but mu 0 I over 8 pi square are all constant, and then here we should have r squared, and then cancel with this r, so that it becomes 1 over r. So 1 over r dr over r, and then we should integrate from a to b, and then d theta, we don't have theta, but it should be integrated from 0 to 2 pi. So you can regard it as integrating 1 to d theta, and then also dz, and then it tells you that the length should be should be L. So we integrate it from 0 to L. So in this case, this one is lateral log of R, so which is lateral log of B over A. This one is 2 pi, this one is L. So the final answer will be mu 0 I, and then this 2 pi partly cancel with this one, which become 4 pi, and then we put L here, and then lateral log of B over A. I should have a square here. Okay, so this is the question for this for part A. This is the answer for part A. And yeah. And then for part B, what is the source energy per unit length? So we should calculate UB over L. So we just move this L over. So we have a UB over L with the remaining terms. So we have mu 0 I squared over 4 pi, and then lateral log of B over A. So mu 0 is 4 pi times 10 to minus 7. So it is like this, and then times I is 2.7 squared, and then natural log of 3.5 over 1.2. So this number is nothing but 7.8 times 10 to minus 7 joule per meter. Okay. Okay, any questions? No questions. Let me finish the last one. So here, it says two parallel loops of y have a common axis, this one and this one. So the smaller loop is above the larger loop by a distance x. This is x, the distance between them. Consequently, x is much larger than capital R. And then consequently, the magnetic field due to the counterclockwise current. So we have a counterclockwise current here. And then in the larger loop, it's nearly uniform throughout the smaller loop. Okay, so we suppose that the magnetic field here is nearly uniform because this x is quite large. Okay, so and then suppose x is increasing at a constant rate v equals, so it is the velocity. So we'll find an expression for the magnetic flux through the area of the smaller loop as a function of x. Okay, so this is a magnetic dipole, and then if we assume x is or z is quite large, so in this question this is x, but in the previous chapter we use z, so we just change z to x in this question. Okay, so here we write it as B equals mu0 over 2 pi, and then this mu is I times a, so I times pi capital R squared, because this is the magnetic dipole with the current, so we use pi capital R squared, and then over x cubed, like this. Okay, so 5b, of course we are talking about the 5b here, so 5b will be approximately b times a. A is referring to this cross-section area. So we have mu0 over 2 pi and then times I pi r squared over x cubed. So this is the b, and then a of this one is pi small r squared. Then we can slightly cancel the pi, and then write it like mu0 pi mu0, and then I small r squared capital R squared over 2x cubed, like this. Okay, so this is the magnetic flux. This is the magnetic flux for this question. So this is the answer for part A, and then for part B. It asks find the expression of the induced EMF. So we can make use of the Faraday's law, which is E equals negative d phi b dt. So in the previous one, we already find phi b to be this expression. So we just need to plug this expression here. So negative d dt, and then we have pi mu0 I r squared capital R squared over 2, and then we have 1 over x cubed. So we note that these one are not related to t, so we can just put it out. We have a pi mu0 I r squared capital R squared over 2, and then we have a d dt 1 over x cubed. Okay, so even though this is not x, but x is a function of time, so we need to take care of this derivative. And actually, it should be negative pi mu0 I r squared capital R squared over 2, and then this one this one is actually x to the negative third power dt. So it should be negative 3 over x to the fourth power and then dx dt. This is a chain rule. Yeah, this is like this. So we have a negative 3 over x to the fourth power and then times dx dt. And this one is of course v. So finally we can write it as 3 pi mu 0 I r square, capital R square v over 2x to the fourth power. Okay, so this is the expression for part B. And then for part C, it asks you the direction of the induced current. Okay, so in this case, we can see that for this loop, the current is counterclockwise. Which means that the B field is pointing upward. So pointing upward is a positive direction. And you can see that this loop is moving away. Which means that the magnetic flux going through the smaller loop is decreasing, which means that the induced EMF should point to this side. So which means that the direction of the induced current should be counterclockwise. So this is for part B, and for part C, the induced current should be counterclockwise. Okay, so I think that's the end of this chapter, and see you this Thursday. We'll have midterm exam.